So our next lecture in our learning unit on electrochemistry really only involves one type of skill and one type of problem, only a couple of homework problems to practice this, but that is learning how to diagram a voltaic cell. And so conceptually, we need to think about this like a puzzle. We need to figure out, once we know a redox reaction is occurring, and we separate it into two compartments, we need to be able to label a diagram to tell us what that voltaic cell looks like. So some things that'll help us, kind of some mnemonics and so forth that'll help us for today are remembering the phrase an ox and a red cat. And that is going to tell us that the anode is where oxidation occurs, and reduction is going to occur at the cathode. And I've used a plus sign in place of the T here on the cathode because that also reminds us that the cathode is going to be positively charged. So we're going to run through a little bit of buildup here to help us think about how all of these puzzle pieces fit together, and then we'll wrap up this lecture working through one problem on how to diagram a voltaic cell. Keeping in mind, you may need to work these kinds of problems both forward and reverse. We're going to work the problem in the forward direction where you're given a redox reaction and you have to diagram the cell, but you also might be given a fully diagrammed cell and you need to know how to back out the chemistry that's going on in that voltaic cell. Okay, so I'm going to start here with the slide that's just a little bit of a review on some of the chemistry that we've talked about in our last lecture, where we just learned about redox reactions again, refreshing our memory on that, and learning how to think about creating balanced redox reactions. That's an essential skill that gets built on in this next section because we do need to have balanced redox reactions in order to move forward. So we're going to spend kind of, as we build up our understanding of voltaic cells, we're going to use sort of this basic redox reaction here, where we're going to have solid zinc. Here we have solid zinc in our oxidation reaction. Zinc is going to be oxidized, meaning it's going to lose 2 electrons to become a zinc cation. So we can see everything that's in red here is going to highlight the oxidation process. So again, zinc becoming zinc 2+. Here we can see the zinc oxidation half reaction here. So in our half reactions, remember we show electrons in our half reactions, but our electrons don't appear in our overall balanced chemical equation here. And even to this end, we don't have any spectator ions, right? We might be able to see elemental zinc, but we can't see copper as just copper 2+ on a shelf. It would be with some type of a counter ion, probably a nitrate or a chloride or something that, as we're going to learn later, does not have any redox capabilities. All right, so keeping with our oxidation reaction here, let's kind of look at what happens from a pictorial standpoint here. So if we've got solid zinc, that's what's represented sort of by this green, by this red bar here, or this bar here. So if we're starting with elemental zinc, we're going to have this piece of zinc metal that's sitting in a solution here that's blue, and we're going to get to why that solution's blue in a second. But what happens here, we can look at this and from an elemental standpoint in this atomic scale, we're going to have zinc here that loses an electron and becomes zinc 2+. So one of the things hopefully you remember from Gen Chem 1, I'm going to do my best here as we move towards the end of the semester to help review concepts from previous chapters. When we take an atomic zinc in its elemental form and we make it into a cation by losing 2 electrons, that atom becomes smaller. So thinking about trends in atomic size, that was something we talked about in Gen Chem 1. But zinc, again, losing electrons, becoming zinc cation, is our oxidation reaction here. And so on a kind of a macromolecular scale here, we can see that by having our elemental zinc bar here in solution. And what happens as this reaction proceeds is we're going to see that zinc bar actually gets smaller and smaller. It's going to go away because that zinc is being converted into zinc ions in solution. Here you can see a lot more zinc ions in solution. So zinc ions in solution are represented by these little gray spheres here. All right, so that's our oxidation reaction here. Remember, oxidation, the loss of electrons, doesn't happen without somebody being willing to gain them. And so in this redox reaction, It's copper. Copper is our reduction reaction. So what we have here is we have we have ionic copper, copper 2 plus ions. That's why the solution is blue. Copper ions are actually blue in color. So we're going to have these copper ions gaining electrons to become elemental copper. Okay, so that's everything that's shown in green here. So again, let's start here on our left here. Here we have our copper ions, which are blue in solution. So they're just kind of represented here by this copper ion. You'll notice here that part of these two red and green lines overlap, and that's this part where we're trading electrons. So the zinc sort of gave up 2 electrons. Copper is going to take on those 2 electrons. That copper ion is going to take on 2 electrons and become elemental copper or solid copper. And here we can see that when we take this cation and gain electrons and become elemental copper, that atom actually becomes bigger in size. So what we see over here on a macromolecular sense on the product side is we actually see the accumulation of elemental copper. And so we see, and we're not going to get into too many details about why it looks black in color, but that is elemental copper that's appearing here. So one of the things that you also can see here is that the copper ions are blue in solution. So this solution actually becomes less blue as those copper ions are disappearing from solution. So again, that's information that we've talked about already in terms of putting things together in terms of a balanced chemical equation. Remember, with our balanced chemical equation here for our redox reaction, we don't see the electrons because those electrons are going to be canceling out. So one thing that's unique here is when we throw everything together sort of in the same mixing pot, those electrons are immediately transferred from one species to the other. So there's no ability to harness the energy of those electrons to do any work. And that is sort of the key to what's going to happen when we build what we call Voltaic cells, okay? And so these electrochemical cells, and again, they come in 2 flavors. We're going to focus kind of on Voltaic, or what are called galvanic cells. These are what batteries are. The main difference between these 2 types of cells are which direction energy is flowing. So if we take this copper and this zinc sort of system and we separate it and allow the electrons to flow through a wire, we can actually harness that energy to do work. And that's exactly how a battery works. However, if we wanted to run this reaction in the reverse direction, and for example, we wanted to make elemental zinc and we wanted to take copper and force it to give up its electrons, we'd actually need to put energy into that system. And that's what we call an electrolytic cell. We're not going to do too much with these cells. We will talk about them a little bit qualitatively, but these are going to be non-spontaneous reactions. So we're going to need to put energy in, and this is what happens, for example, in electroplating. So if you have some silverware that you're going to electroplate it, so you take a less valuable metal, that's kind of the core of a piece of silverware, and then you take silver ions that are in solution and force them to be silver metal on that piece of silverware. That's what we call silver electroplating. But you need to put energy into that system in order to get it to work. All right, so here's just some pictures, again, highlighting the difference between these 2 different types of electrochemical cells here. So we've got a Voltaic cell. This is the one we're going to focus on. And what we can see here is we're going to split the half reactions into 2 separate compartments. And rather than them being able to trade their electrons directly in the shared solution, their electrons are going to have to pass through a wire. And by passing the electrons through a wire, we are able to harness the energy of those electrons and be able to do work. Okay? That's different in an electrolytic cell, for example. If we're going to do chemistry in an electrolytic cell, we actually need to supply power in to have this process happen. And you'll notice this process sort of happens in the same solution here. We're not going to have too many problems that we'll work through with an electrolytic cell, but we're going to supply energy in, and we're actually going to get some of those metal ions that are in solution to be plated out on one of the electrodes, and that's how we do electroplating. But let's focus here on the Voltaic cell. That's what today's lecture is going to be about. Okay, so again, we're going to have oxidation reactions occurring in one half cell. So we call these half reactions, but we actually split them up into their own separate compartment. By formalism, we're always going to write the anode on the left and the cathode on the right. So again, highlighted in blue here, we're going to have the oxidation half reaction. Remember, oxidation is the loss of electrons, so there's those electrons there. This is why we learned that little phrase, an ox and a red cat, at the beginning of lecture, because this reminds us that the anode is where oxidation occurs. So whether you want to remember that the anode will be on the left or the redox reaction, that is an oxidation half reaction, occurs on the left, both of those occur on the left side. Red cat reminds us that the cathode is where reduction occurs. And remember, I used a little plus sign for my T in spelling of the word cathode, and that reminds us that a cathode is going to be positively charged. So these are going to be the things that are always the same for every single voltaic cell. Anode is on the left where oxidation occurs, and that electrode will be negatively charged. Cathode appears on the right, that's where reduction occurs. That electrode will be positively charged. Electrons always flow from the anode to the cathode. So here we can see electrons lost in our oxidation half cell are going to flow to our reduction half cell. And they do so through a wire. And that allows us to harness that energy of that process. We'll talk about in a little bit what this little guy is here, but that helps to balance charges. Okay, so that's how we diagram a voltaic cell. So let's take this chemical reaction that we kind of learned about at the beginning here, and rather than having it occur just all in one pot, let's imagine that we separate these two half reactions into two half cells. Okay, so again, we're going to separate these half reactions into two half cells. So again, these voltaic cells are going to take and put the oxidation reaction, which is where the anode is, on the left side, and then the reduction reaction, again where the cathode is, on the right side. So again, here was where we remembered from our first problem that the oxidation reaction was zinc going to zinc 2+ and releasing 2 electrons, and then the reduction half reaction was copper going to make copper metal by gaining 2 electrons. Okay, so I know there's a lot on this slide, but I want you to sort of just see this as a puzzle that you put these pieces together in. Remember, some things are always going to be the same. Anodes on the left, cathodes on the right, electrons flow from left to right. So that again is a formalism that will always be the same. And then we need to mix in what is specific to our unique redox reaction. Well, we know from our redox reaction that our oxidation reaction is the zinc half cell. So that's going to go over here. Now, if you have something that's a pure metal, you can actually use that directly as your electrode. So we always need to have electrodes on both sides here. Those are going to be where that oxidation or reduction reaction happens, is at an electrode. With this specific example, we're taking zinc metal and making it into zinc ions, so we can actually have our electrode be that redox active metal. Same thing over here with our cathode on the right. Because we're actually going to be making copper metal, we can have the electrode for this half reaction that happens in the cathode be copper metal. As we'll see when I go through one more example before we do our problem, sometimes the redox chemistry that you might be doing doesn't involve an elemental metal. In that case, you actually have to choose something else for your electrode. We'll get to that in a little bit. Okay, so if we know that this is our oxidation half reaction, the solid metal can be our electrode. If this is our reduction half reaction, the solid metal that's formed can be our electrode. Okay, so now we have to figure out what's going to go into the aqueous solution that we have here. Well, if we're considering the redox active species, the whatever species is going to be our ion in solution is going to be our ion in solution over here. So we're going to have zinc ions over here, copper ions over here. But notice what's unique and different here. We don't necessarily need to start or have zinc ions over here because they're going to be made. We are going to be making zinc ions over here as zinc becomes oxidized and loses its electrons. So we're not going to necessarily start with zinc ions in our solution. They're going to be made. Its concentration is going to be increasing. On the other hand here, note that we have to have copper ions in solution for our reduction half reaction because that's a reagent. We have to have copper ions in solution here. And as this reaction proceeds, these copper ions are going to decrease in concentration. Okay? So again, we don't have zinc cations to start with. They're going to be made in solution here. But we do have to have copper anions to start because that's part of a reactant. You will note here that we do have copper metal to start with, but that's because we had to have an electrode to have this process work here. All right, the last piece to consider here is this little guy that I said we're going to get to in a minute. This is called a salt bridge. Okay, you'll notice here that sodium and sulfate are not anything that participate in redox chemistry, right? We don't see these as part of our balanced half reactions here. But these guys are important because this battery could not work if we did not balance ions. So see if this puzzle, part of the puzzle makes sense. We are going to be increasing the concentration of positive charge in our anode compartment. That's why sulfate is going to migrate over to this side to help balance that charge. We're increasing the concentration of positive ions, so negative anions are going to migrate in this direction. Let's see what happens on the flip side here. In this case, we're going to have the positive charges being decreased here. In that case, we need to replace them. So positive charges are going to move over from the salt bridge to our cathode compartment. Okay, so our salt bridge is always going to be moving ions. They're actually going to be moving our spectator ions, whatever the spectator ions are that we have in solution, whatever the cation and anion were. Maybe it's nitrate, sulfate, potassium, or sodium here. These guys, they're always going to move in the same direction. So if you want to, you can think about that the anode's always negatively charged. We're actually going to be moving anions over to that compartment. Cations move over towards the cathode. That's always going to be the case, but you might need to identify, well, what are the spectator ions that are going to be moving in my salt bridge? All right, so that was a lot of information there. There's a lot to diagramming a voltaic cell. But again, hopefully you see this as a fun little puzzle to kind of put all the pieces together with. So let's take this one and just dissect a little bit further because some of the qualitative questions you might see related to this kind of section of our chapter on electrochemistry might involve asking questions about what happens to the charge or the mass of this electrode? What happens to the concentration of ions in this solution? So let's take each half cell and sort of break that apart. All right, so again, what I'm doing is I'm taking this same picture that we just walked through, but we're going to talk about some details of the left side and then of the right side. So let's talk about our anode compartment. First, again, that's where oxidation occurs. That's where we're going to have a zinc metal bar as our electrode. We need to have we're going to actually generate zinc ions as our electrolyte in solution. Remember, we don't start with any zinc ions in solution, but they're going to be generated through our chemical reaction here. Again, we can see this chemical reaction here. So zinc, that's part of our electrode, is going to lose its electrons, and it's going to generate zinc ions in solution. So asking questions about sort of what happens here, we're going to see that the zinc electrode is actually going to lose electrons, and it's also going to lose mass. Here we can see a picture of what that zinc electrode looks like after we've let this chemistry proceed for a while. It actually gets smaller, and that's because some of that solid zinc that we could physically see becomes zinc ions in solution. Okay, and again, just some pieces that we already know, but stating them here again. Electrons are again generated at the anode because that's where oxidation occurs. That's why the anode is negatively charged. Now, I know it can be a little bit confusing because those electrons are actually going to leave and go towards the cathode, but this bar becomes negatively charged because that's where electrons are being generated. All right, so let's go through the same sort of discussion with our reduction half cell. So that's the right side. That's in this case where we had our copper electrode, right? So we had a bar of copper metal that was there. In this case, we needed to have copper ions in solution. We needed to provide those in solution because that's where we were going to have those copper ions gain electrons. So again, these copper ions here that we see in solution are going to be coming close to this electrode and gaining the electrons that are flowing through it. And by gaining those electrons, they're going to deposit copper ions, solid copper, on this electrode. So we can see here that this electrode actually gains in mass. And when we separate these half reactions, we can actually see that we do see that orangish copper metal plating out on that electrode. So again, copper is going to gain in mass. That electrode is going to become heavier. That's one of those qualitative questions you might see on an exam question, is asking, will this electrode increase or decrease in mass? And again, highlighting, since electrons are accepted at the cathode via reduction, the cathode is actually positively charged. Okay, so really, again, what's going to be happening here is we're taking and we're pulling positive charges towards that electrode, so that electrode becomes positively charged, and we're going to attract then those electrodes, or those electrons, coming from the oxidation reaction. You'll notice here, and I'm going to flip back to the other slide just in a second, the copper that we have in solution was actually generated from copper sulfate, and that's where we got those copper ions here. We're going to see here zinc sulfate is going to be in solution here, because remember, sulfate is what's going to be coming over here. All right, so kind of putting this all together and looking at this overall picture again and highlighting what happens with this salt bridge, we're going to have an imbalance of charge that's going to happen because of this redox chemistry, right? We're going to be increasing the concentration of zinc ions in solution, decreasing the concentration of copper ions in solution, and this reaction would rapidly halt if we didn't have some way of maintaining this electrical neutrality. So that happens through what we call a liquid wire. We're actually going to have a physical solid wire, a metal wire that the electrons flow through. But these cations are going to flow, or these anions are going to flow through this salt bridge, which helps to neutralize that imbalance of charge that's going to happen because of the separation of these two redox reactions. So again, reduction again occurring at the cathode. We're going to be depleting cations from solution, so we need to replace them. Oxidation, right, is going to be occurring at the anode. In that case, we were actually going to be adding cations to solution here, and so we're going to balance that charge by having sulfate actually come over here. And so again, that movement of those anions and cations is always going to be in the same direction. We're always going to have anions go to the anode, cations go to the cathode. And so again, if that's something that you just kind of want to memorize or remember, that's fine, but you should be able to do a logic check and see that that makes sense. All right, so just a couple other ways to sort of highlight how we can show this process, and I want to show you sort of a formalism, sort of a shorthand notation that I do want you to know. Okay, so if we kind of show what's happening here, again, here's our oxidation half reaction, our reduction half reaction. This is showing the same thing but without the picture. We're going to have electrons flow from our anode to our cathode. We're going to have cations flowing over to our cathode, anions flowing over to our anode. And so this is just sort of a semi-shorthand way to sort of diagram that voltaic cell without physically drawing the voltaic cell. And again, this still shows anode on the left, cathode on the right. So this is kind of getting a little bit shorthand here, but still sort of diagramming everything that's going on. So I want to take a second here and highlight this concept of inactive electrodes. So let's imagine we had this redox chemistry, right? What if we had iodide being oxidized to iodine, so elemental iodine here. And then in our cathode half reaction, we're going to have permanganate being reduced here to manganate 2+ cations. Okay, so pretty complicated sort of half reaction here, though, in order to balance it. But again, if we had these two things, you'll notice that there's no elemental metal there. So this redox reaction can still occur. All of these guys would just be species that were in solution here, but we would have to have an inert electrode that's sort of acting as the meeting place, if you will, for all the parts of these redox reactions. So again, in the one that we just spent a good bit of time on, that copper zinc voltaic cell, the electrodes are what we call active. They are participating themselves in the redox half reactions. We don't have a metal to participate in these two redox half reactions, so we will use inactive electrodes. And if you are diagramming one, you can choose. You can choose a carbon graphite electrode or a platinum electrode. Either one of those will work. Again, and we use these when there are no reaction components that can be used as an electrode. So again, when we have nonmetals or ions that are participating in redox chemistry. But note what happens here. We do see in this process, we see, remember, iodine is a solid here. So when this chemistry happens in the oxidation half reaction, so when we have iodide being oxidized, losing electrons and becoming elemental iodine, we actually are going to accumulate that. Remember that the electrode serves as the meeting place for this chemistry to happen. So when these iodides kind of come close to the electrode and they give up their electrons, they become iodine, that elemental I2 solid. So we're actually going to, have that accumulate on this electrode. So I wanted to point this out because don't always assume that, remember, let me flip back here for a second, that this electrode got heavier. Right? We can see that. Sorry, I'm flipping all around here. The copper electrode is the one that got heavier. That was the one that was on the right. That doesn't have to be the case. Here's a case where the anode is actually going to get heavier. So that's not one of those pieces to memorize. You have to understand the chemistry that's going on. And in this case, the product of the oxidation half reaction is a solid. So that's going to be kind of precipitating, I shouldn't say precipitating, plating out there on that electrode. All right, so let's think about how we actually go through a systematic way of diagramming these cells. Okay, so again, there's going to be some things that are always the same. So half cell components always have electrodes that you have to identify, electrolyte ions, and any other species that we might have, like the species that are participating in a salt bridge. Okay, electrodes are always going to be in the same spots. So the anode's going to be on the left, cathode on the right. But again, you might need to identify what you're using as the cathode and the anode. Do you have a redox active metal that's going to be participating in your chemistry? Or in this case, we actually have to use inert electrodes. And you could write C for carbon or PT for platinum. Either one of those could work here. Okay. Again, you might have to do some stuff like we did in our first lecture. You might actually need to balance our half reactions and determine a balanced overall redox reaction. You might need to do that balancing in order to figure out what's going on in these redox half cells. So again, this is sort of like a skill. I'm going to kind of write this down here. This is like a lecture 1 skill. You might need to know how to do that in order to move on with this diagramming. Again, some things that are always the same here, we're always going to see that electrons flow from left to right. And again, we're always going to see for salt bridges, anions moving to the left, to the anode compartment, cations moving to the right. So there are some things that are kind of always going to be universal. So let me go ahead and sort of highlight these things that are unchanging. Direction of electron flow is always the same. Kind of putting things in different components is always the same. And movement of things with salt bridges is always the same. And again, where we have our cathode and our anode, those are sort of always the same. What becomes unique is the identity of what's in those different compartments. So again, let me just highlight here on our notes here. These things are always going to be the same. Where, the direction that electrons flow, where ions flow from our salt bridge, where we put the cathode and the anode are always going to be the same. Okay, so last thing I want to show you before we run through one example that I want you guys to try to practice, and kind of I'll reveal it in stages on the video here, is to highlight that we do have a shorthand way of writing half cells. So you are likely to see not only homework problems, but exam problems that just show you something like this. And they say, diagram this half cell. Okay, so they're going to show you something that just looks like this. All right. What we need to remember is this represents what's going on in the anode, which is our oxidation chemistry. This is what's going on in our cathode. This is our reduction chemistry. If there's a phase change, they just indicate a single line here. So again, we've got solid metal and we've got zinc here. Keep in mind that there's no distinction with what's written on the left or the right necessarily, but the line here indicates phase changes. Double lines tell us that we're separating components between our anode and our cathode. And so you might need to take information that looks like this and put it together into a voltaic cell diagram that looks like that. Okay? All right, so here's what that shorthand notation would look like for the one where we have the inert electrodes. And again, you have to specify what the inert electrode is. You could write carbon here, but carbon is also a graphite electrode. And again, we've got our iodine, or our iodide here, and then our solid iodine. And then in this case, these are all ions in solution here. So anything that is multiple ions in solution, we just separate things with commas if they're in the same phase. And again, we've got a graphite electrode here. So kind of a formalism that they do tend to use is they show electrode first, redox active components, break between your different half-cell components, and then again they show redox active components and electrodes. So the shorthand notation is often bracketed by electrodes on the far ends, but again, I'm not going to be picky about that. All right, you ready to try one on our own? So this is a sample problem. I think it's sample problem 20.2 that's in your textbook. How to diagram a voltaic cell. So again, this has a lot of information it's asking us to provide. It says draw the diagram, show balanced equations, and then write the notation for a voltaic cell that consists of one half cell with a chromium bar and a chromium nitrate solution, another half cell with a silver bar and a silver nitrate solution, and they tell us that we've got a potassium nitrate salt bridge. Now, this is an important piece of information that they give us with this problem. We'll actually learn in our next lecture that we could have figured out who was the anode and who was the cathode, but because we haven't learned that yet, they give us a little piece of information here that tells us who's being oxidized and who's being reduced. Okay, so I want to highlight that you'll always be provided sort of a diagram. It looks like this. Okay, oops, I had some answers there. It looks like that. You'll actually be provided with that skeleton diagram, so you don't need to worry about drawing that, but you will have to label all the relative pieces. So I'm going to walk you through sort of a 3-step process here for how to do that. The first thing is we're going to label any pieces that are going to be the same for any problem. That's identifying the anode, the cathode, the direction of electron flow. And again, once you've identified the anode, you know where the oxidation half reaction occurs, and you know that that electrode is negative. Same thing for the cathode. That tells us where the reduction chemistry happens, and again, it tells us which electrode is positive. So that's always going to be the same. The next thing you need to do is you need to look at who's in solution and then break those things apart to determine your half reactions and your overall chemistry. Now this could be something that we're going to build on the skills that we had from our first lecture. Remember, we sort of had to pull apart and identify who looked like they belonged together in a half reaction. And again, we might need to have some help from information in our problem to help determine, for example, which is the oxidation and which is the reduction reaction. And what I've highlighted in blue here is that information that helps us, right? It tells us that the chromium electrode is negative relative to the silver electrode. So that tells us that chromium is where oxidation is occurring. Okay, so that's going to be an important little piece to our puzzle. Once we kind of start building up the kinds of chemistry that's going in solution, then we basically need to make sure we assign everything to the right compartments, to the right solutions, answer questions about what might be going on in solution, which electrodes getting heavier, are concentrations of this species increasing or decreasing, and so forth. So let's go ahead and start this problem. The first thing I want you to do is try to, if you were given a blank diagram, and there are blank diagrams that are available on Blackboard, you can just kind of download. It just says a voltaic cell blank diagram. Try labeling the things that are same for any problem. Where are these things going to be? So again, I'm going to pause the video periodically here, encourage you to pause it so that you can try to work through this solution. All right here. So again, anything that's going to be the same for any problem is what I've shown here in blue. Again, we know that the anode is going to be on the left. That's where oxidation occurs. This electrode is going to be negatively charged. Cathode is going to be on the right. That's where reduction occurs. This electrode will be positively charged. Electrons always flow from right to left, and I didn't draw it on here, but we could always say that anions are going to flow to the anode. Cations will flow to the cathode through our salt bridge here. And they did tell us the identity of what our salt bridge was. They did say that we've got a potassium nitrate salt bridge, so we'd know in that case that nitrate's going to flow this way, potassium's going to flow that way. So there is one other thing that we could add on this before we actually knew anything about the chemistry going on. But that kind of gets us started here. The next part is probably the most challenging because we need to think about splitting up all the pieces of information they gave into an oxidation half reaction, which will occur on the left, and a reduction half reaction that'll occur on the right. So again, they gave us some pieces of information here. They told us that the chromium chemistry is going to be occurring at the anode because they tell us that's the negative electrode. So look at the species that we have in solution, right? And see if you can figure out what the two half reactions are that are occurring in each half cell. All right here. So again, the second step is to say, all right, who is in solution? And then determine the half reactions and the overall chemistry that's happening. So again, we knew that we had chromium nitrate, we've got silver nitrate, potassium nitrate, and then obviously they told us we've got a silver electrode and a chromium electrode. So because they told us that the chromium electrode was negative, we do know now that the chromium is what's going to be in our oxidation, our anode compartment. And so if we write chemistry based on the species that we're given, we know that we have chromium 3+, and we've got chromium as a solid because that's our active electrode. Chromium going to chromium 3+ is going to lose 3 electrons. Note here, we know we can't write it this way, right? Hopefully we recognize we can't write this chemistry, even though we know the chromium electrode is on the left and this is chromium chemistry. We know that this can't be the chemistry that happens because this is the anode compartment. Anode is where oxidation occurs, so this part can't happen. All right, so here's our oxidation half reaction. So that must mean that silver stuff is going on in the cathode compartment. All right, we know we've got a solid silver electrode, and since we know it's reduction, we know that the electrons have to be on the left side as a reactant. So that must mean silver ions from our silver nitrate solution are going to gain electrons and become silver solid. Note here, and this is where we bring in skills from our first lecture, in order to have this be a balanced chemical equation, we have to scale up the number of electrons that are gained in our reduction half reaction to match that are lost by our oxidation. So we have to scale this guy up by 3, and doing that is going to give us our balanced overall redox equation. That was one of the things that this problem also asked for, was a balanced chemical redox equation. The last thing that we want to do is label everything that's going on in here. And I want you guys to pause for a second and see if you can figure out what to label in here. All right, if this is our redox reaction that occurs in the anode compartment, so it's oxidation, that must mean, again, we know that our chromium electrode is going to be over here. We know that our chromium 3+ ions are in solution there. If we were to address some questions about how would the concentration or the masses of these be changing, the mass of this chromium electrode would be decreasing because those chromium metal atoms are becoming chromium ions. So again, the concentration of chromium is going to be increasing. Let's go over here to our silver. In our silver compartment, again, we know that our silver electrode is going to be taking silver ions, combining them with electrons to make solid silver. So that means the mass of that silver electrode is increasing. And that must mean that we're depleting silver ions from solution, so that concentration is decreasing. The last thing to sort of put in here is this concept of where are our salt ions moving. So they told us we had a potassium nitrate salt bridge. And again, you can remember that anions go to the anode, or always have a logic check. Understand why, because that way you don't need to worry about memorizing it backwards. We're going to be increasing the concentration of chromate ions in solution here, which means this is becoming more positively charged. So we need to combat that by moving more negative charge over there. On the flip side, we're decreasing the positive concentration over here because we're removing silver ions from solution, so we need to replace them with potassium ions to maintain that electrical neutrality. So the last little piece that we have up on top here has us diagramming that voltaic cell using that shorthand notation. So all it really shows is the redox active species in the correct compartments. And again, that's just going to be a way that tells us who's in which compartment. And again, we usually bracket the outsides of these with what our electrodes are. All right, so a lot of information there, but hopefully you sort of see it as a fun little puzzle to put together to figure out what does this voltaic cell look like. So again, so the only thing we really worked on today is, again, diagramming a voltaic cell. We need to be able to separate redox reactions into their respective compartments, understanding that oxidation half reactions occur at the anode, so remembering NOx. Remembering that that is going to be where our negatively charged electron is. Electrons are going to be lost here and flow out to the cathode. And again, I'm going to highlight here, in general, we're going to have electrodes lose mass here. But remember, with our situation with our inert electrode, with our deposition of our iodine there, we actually saw that that electrode will gain mass. So this is true that this electrode will lose mass if it's an active electrode. But if it's an inactive electrode, it may not be the case. Reduction reactions occur at the cathode. That's why we had an ox and a red cat be what we remembered. Cathode, again, that T reminds us that the cathode is positively charged. Electrons, again, are going to be gained here that are coming in from the anode. And so this electrode, again, if it's an active electrode, will gain mass. So big skill, be able to diagram a voltaic cell and know that shorthand notation, but also be able to go in the reverse direction, be able to look at a voltaic cell and kind of pick out information with stuff that's going on.